spectrum analysis and just why it's important, what it is. And again, just for my benefit, how many of you guys have, or ladies have used spectrum analyzers or signal analyzers in one form or another? Okay, great. So sounds like there's a high degree of familiarity with it, so that'll help us cruise through these a little bit faster. But we will talk about the difference between spectrum and signal analysis, what measurements these analyzers are capable of. We'll talk about the theory of operation. Even many long-time users of these instruments don't always know what's inside and how it all works together. We'll talk about some of the important specifications. We'll talk about modern signal analysis designs and hardware and what's in there, and then we'll have the wrap-up. Okay, so for the purposes of this presentation, a spectrum analyzer essentially allows you to look at the amplitude versus the frequency of a signal and display that. When we talk about a vector signal analyzer, it has that capability as well, but instead of being a magnitude-only analyzer, we actually add some phase capability. And we talked about that a little bit in the last presentation, but we are able to add some phase information to that to do things like digital demodulation, where we can measure things like error vector magnitude. And then a signal analyzer combines functions of both a spectrum analyzer and a vector signal analyzer. So for this talk, I might use the terms interchangeably, kind of a slip of the tongue, but in our literature, you'll kind of see those differentiations made. So if you haven't used a spectrum analyzer before, this is what they typically look like. You have usually color screens for the modern analyzers. You have various input buttons here, and then this is what it looks like. So just to tie together some of the concepts we saw from the last presentation, here we see a CW signal as represented on a signal analyzer or spectrum analyzer, so you can see kind of a single tone, and then you see the skirts here, and then this is just the noise floor essentially of the instrument. Here we're looking at what seems to be a digitally modulated signal. Some people call it a Bart's head in honor of Bart Simpson, right? But here's where the information is being modulated, and then you have the skirts and then the noise floor. And then this looks like some sort of pulse signal. So here you can see the main lobe, and then here you see the sine X over X response there. So a spectrum analyzer can give you all those plots. So for those of you who have not been exposed to any sort of spectral analysis before, maybe you're used to seeing things on a scope or in time domain, or you've repressed any and all knowledge of Fourier analysis, right, from college or school. We're going to give you a couple of slides on this. So if you're looking at a signal, let's say in terms of time domain, as you would on a scope, you might get a signal that looks something like this. So that's nice as far as it goes, but it really doesn't tell you how this signal was created, right? It's not a sine wave. It doesn't really fit any nice mathematical equation, right? So what we're able to do inside of a spectrum or signal analyzer is we're basically able to take these periodic signal that looks something like this and decompose it into its various frequency components. So here you can see in the picture that this is basically a summation of these signals here. So here you can see my red sine wave, my green sine wave, my purple sine wave. And if you looked at it on a spectrum analyzer, you can think of it as kind of looking at the side view of these guys, but this is what the red sine wave would look like, the green one, and the purple one there. And so these would all be at different frequencies. So again, just as an example, this could be 1 gigahertz, 2 gigahertz, 3 gigahertz. It would tell you the amplitude of each of the signals, not only absolute amplitude, but the relative amplitude to each other. And then it also tells you the actual frequencies of each of those. So to bring this into a little more clarity here, let me this one. Let me just run a little graphic. And what you'll notice is each of the blue lines, which are spectral tones, rotate at different rates. So that would be analogous, basically, and it's how it happens. So these are the different frequencies. So again, this might be 1 gigahertz, 2 gigahertz, 3 gigahertz, 4 gigahertz. So so the fundamental here has less cycles, right, than this little guy here, which you can see is spinning around quite rapidly. So again, this refers to the frequency of oscillation. Again, pick 100 megahertz, 200 megahertz, 300, 400 megahertz, whatever you wish. But when you add each of these frequency components individually, they all add up to the red signal here. So this being time and this being frequency, you can kind of see how those two tie together. One last time. And if you're familiar with any of our application notes, the golden one, kind of the standard for the industry is something called, I think, App Note 150, written by a gentleman named Blake Peterson. And he was the guy that actually put a lot of these little programs together. You can see 1998. So that's a lot of work there. So anyway, hopefully this helps establish the relationship between time and frequency domain there. So back to the show. So in modern signal analyzers, these instruments are capable of quite a few different analyses and measurements, not just spectrum or Fourier type analysis. Just familiarize yourself with them if you haven't been exposed to it before. They can make noise figure measurements on amplifiers or even frequency converters. They can make phase noise measurements, so we talked about that in the signal generation presentation. So signal analyzer is a very capable instrument there. It can look at the harmonic distortion of a signal. So let's say your circuit's putting out what you think is a 300 megahertz signal. We're able to see all the harmonics of that as well as all the subharmonics of that on a signal analyzer. We talked about in our signal generators how they can generate analog signals, digitally modulated signals, and pulsed signals. Again, the spectrum analyzer or signal analyzer can look at those signals and give you all sorts of information about that. And as well as vector analysis. So you can see the measurement range as far as these different signals go is between minus 172 dBm all the way up to 30 dBm. We'll talk about this in a little more detail. So thermal noise floor is roughly minus 174 at room temperature. So you can, and we can actually get there with some enhancement techniques that I'll be talking about, but we can get way down there, right? And then 30 dBm is the damage level. So unless you put some sort of attenuation in front, this is kind of the damage level of instrumentation. So hopefully you can see that's a very wide range of signals that we can look at in terms of power level. And then in terms of frequency range, we almost go down to DC. And then with some millimeter wave modules, we can actually go as high as 325 gigahertz. So anybody in here exceed those parameters? Okay, just checking. So there's really two types of analyzers that have existed over the years, and to be honest, most of our modern analyzers kind of have both of these functions built into them, but it's useful to just talk about them. So one is just an FFT analyzer. So the way you can think of an FFT analyzer is you just have multiple parallel filters operating simultaneously. So if you have two signals, you know, this signal will show up as energy in this filter, and this signal here will show up as energy in this filter. And then you look at the display, and there's two filters there. And so historically, fast Fourier or FFT analyzers were fairly low frequency instruments because the processors just didn't have the processing speed needed to do wider bandwidth. So when these first came out, they were on the order of tens of kilohertz maybe. But over the years, it's megahertz and gigahertz now. So another mental picture, instead of an FFT analyzer where it just kind of looks at the signal simultaneously, is what we call a swept analyzer. So in this scenario, just imagine you have these signals here and you sweep a filter across the whole span. So again, this is amplitude and this is frequency. So when it encounters energy, that filter will let that through, and it sweeps here and it sees this one and it lets that through. And so we can see that signal displayed as well, right? Now, it turns out we don't actually sweep the filter. We actually sweep the frequency, because it's a lot easier to sweep a frequency than it is, or a signal, than it is to sweep a filter. But we'll go through the architecture of this. But those are kind of the two mental models. Lots of parallel filters or a swept filter. So here is our traditional block diagram for a spectrum analyzer. Up until basically 2000 time frame, this was the basic architecture for all spectrum analyzers. So it was pretty much all analog. And we'll go into each of these parts in detail. But essentially, what happens is you have an input signal here. It goes into an attenuator, which helps adjust the input level. Then it goes through some filtering. Then it goes through a mixer. And I got to say this because not everybody is familiar with mixers. But a mixer is typically a 3-input device. And so you have typically an RF port, an LO port, and then that mixes or combines together to create a IF or intermediate frequency at yet a different signal. But it's never just one signal. Usually there's a whole bunch of signals associated with that. So the key thing to keep in mind is just a mixer is a very nonlinear device. So think diodes, think transistors. For a single frequency in, you get multiple frequencies out. So just keep that in mind as we go through the presentation. So the LO from the mixer is controlled by this local oscillator, which is what LO stands for, and that's controlled by this sweep generator. So both the input signal and the local oscillator combine to create the IF signal. Some people think of this as a baseband signal, but then it goes to a whole signal processing chain here. So it goes to a IF gain block, which is typically tied in with the RF attenuator. So the signal stays on the screen when you adjust the attenuator. Goes through some filtering, a log amp, a detector, goes through some video detectors so it looks better to the eye, and then it basically shows up on your screen. So we're going to talk about each of these individually. But first we need a little more terminology. So again, this is a typical screen for a spectrum or signal analyzer. So on the y-axis here we have the amplitude, so that tells you the magnitude of your signal. So here you can see we have a marker on there. So marker 1 corresponds to minus 27 dBm, and if you look at the scale, you can see that's between minus 20 and minus 30 dBm. And this reference level up here that we're referring to right here, that tells you what the signal level is if you had a signal touching the very top line. So you can see that's minus 20. Down here we can see this is a frequency axis. So here's my start frequency, here's my stop frequency. So I can see that with this marker, I've got a signal that has roughly minus 27 dBm in amplitude, and it's at 301 megahertz. And so you could put another marker on this signal, but just from looking at this, it's a 1 gigahertz span, so that I have 10 divisions, so that's 100 megahertz per division. So if I know this is 301, so I can go 401, 501, roughly 600 megahertz. And so most likely this is the second harmonic of this guy, right? So that's how you can kind of look at a spectrum analyzer display. All right. So I've got another animation that'll tie these together even a bit more. But again, this is a mixer. This is the heart of a signal analyzer or spectrum analyzer. And what you can see in this scenario, we have a single frequency in at 1.5 gigs, and then we basically will sweep the L from 3.6 gigahertz to 6.5 gigahertz. And so if you look at the output, or the IF, you'll see basically this is where the F-sig would be, and that's generally at a much lower level. And then you have the LO frequency, and mixers typically have quite a bit of LO feed through. The signals that the spectrum analyzer will process will either be an FLO minus sig or FLO plus sig. And so this is, most folks tend to use a low side signal, and from that we can basically display that on the screen. And again, the animation will make that a little more clear. So that's the mixer. So one of the other parameters that you as a user get to adjust on this is what's called the resolution bandwidth. That's basically the filter width, right? So here we can see for a spectrum, this is what the signal looks like. And so here we're using 3 different resolution bandwidths to look at this signal. So you can see where we have a fairly wide IF bandwidth, we basically get a blob. We know there's something there, but it really doesn't give us a lot of definition, right? We don't know if there's 1 signal, 3 signals, 5 signals. We don't know what's going on. And when you see something like this on a spectrum analyzer, that usually means you're looking at the resolution bandwidth response versus your signal. So what you'll want to do is decrease your resolution bandwidth so that you can get a little more resolution. So here we can see there's a little bit more granularity there. So if we narrow the resolution bandwidth a little bit more, then we can see that there's actually 2 distinct signals. Now, being engineers and technical types, we know there's, you might ask yourself, well, why don't we just use narrow res bandwidths all the time? Well, the reason is the sweep starts to get a lot slower, right? So the sweep speed of a spectrum analyzer is basically inversely bandwidth. So increase your resolution bandwidth by a factor of 10, your sweep speed goes up 100-fold. Okay. On today's analyzers, that's not as big a problem as it used to be, because these guys can sweep really fast. You're talking milliseconds. But we'll talk about some situations where that can enter into consideration. But just keep that in mind. If you want more resolution, you narrow the res bandwidth, but you're going to get a lot of time. So there's that trade-off, right? So after the filter, or like I said, what's often called the resolution bandwidth, there's what we call the envelope detector. So this might be the signal going into the envelope detector, and we kind of depict it as a diode here. But this is what it looks like afterwards, and so you can see it kind of strips off the envelope of this modulated carrier here. So we strip that off for further processing. And so where this kind of comes into play on analyzers is there's a lot of really sophisticated signal processing that goes on the signal on this point. And I'm going to spend a little bit of time here because there's oftentimes misconceptions or misunderstandings about some of the choices that are presented to you on a spectrum analyzer. So typically on a spectrum analyzer, you will choose a certain number of points. And like for our instruments, it's like 1,001 points. Well, people think, well, we're only like taking 1,001 data points. And that's not true. That's maybe the number of points that are displayed on the screen. We're actually taking quite a bit more than that. And when you pick 1,001 points, those are really display points. But what you can think of it as is we're really taking 1,001 bins or 1,001 buckets. And in each bucket, you have several, if you want to think of them as time domain points that are being processed. And so let's say it's 10 points per bin. So depending on the detector that you choose, we will pick out a point out of that bin that corresponds to whatever that detection algorithm is. So in this case, right, if you choose a peak detector or a positive detector, we will look at those 10 data points within that bin, and we will only display the one with the maximum value, okay? So that's called peak detection. Then we have what's called negative peak detection, which will look at that same bin space and pick the lowest value one. We also have something called sample detection, and it's just a sample. So we have an algorithm that says, pick, let's say, the 5th point, right? And we'll just pick the middle point every time, and that's what gets displayed. So if you ever have a chance to get on a signal analyzer or spectrum analyzer, you can play around with the different detector types, and you'll basically see your trace move around. And we'll talk about RMS next. But basically, if you're looking for, let's say, glitches or spurs, you'll typically, let's say, use a positive peak detection. If you're looking at noise-like signals, you'll probably go with something like a sample detection. And RMS power, that really tends to be used in the wireless comms industry or anything that's digitally modulated. So here's a close-up view of a bin. So here you can see, you know, the peak value being picked out, the negative peak value. Here's the sample detection. And then for RMS, what we do is, you can see here, is we basically take the square root of the sum of the squares of all the values that we detect here, run it through the math, and then that's what gets displayed. So when you're making measurements like ACPR, typically it'll be called out that, hey, you need to use an RMS or average detector to make this measurement. Otherwise, you're going to get wrong answers. So anyway, so just these slides are for awareness, but the detector type that you use will be dictated by the type of measurement that you're making. Any questions on that? That's a pretty key point. And again, you'll see that trace move around depending on which detector type. So it doesn't mean any of them are wrong. It's really dictated by the application. And that app note 150 that I told you about, it goes way deep on all of these things. Any questions on that? Okay. So the next part of the processing chain is what we call the video filtering. And it's just what it does just what it sounds like. So you're looking at a video signal, you're getting something noisy, maybe you're near the noise floor and you're trying to figure out, well, what's going on right here? So you can use video filtering, which is, if you want to think of it as the IF equivalent on the video signal, and we'll basically clean that signal up so that you can go from this to this. And it's a separate and distinct setting from our resolution bandwidth. Now, we do relate them, but you can choose them to be independent as well. And so one question we get is, you know, when should I use trace averaging versus video filtering? And you can kind of see right here that the basic difference is the video filter operates real time, right? So as it's sweeping, it's operating right then and there. With trace averaging, you typically have to do multiple traces to see the averaging effect take place. So that may be something you want to do. Most of the time, you'll combine the two. So it's not that big a deal, but that's kind of the difference between the two there. So if you tie it all together, like I said, I've got a little animation here, and obviously this is a greatly simplified block diagram of our spectrum analyzer, but we have the signal going in to the mixer. It's combined with the LO that's being swept across frequency. We get these different frequencies of interest, and it goes to the filter, to the detector, and then this is what we're going to see on our output. So I'm going to run this a few times on the animation, just so you can see what it looks like. Oh, sorry about that. Must be this guy. So basically, kind of what we're looking at here is, this is the signal we're wanting to look at. It's stationary. Here we're looking at the LO. So instead of sweeping the filter, we basically keep the filtering fixed. and we sweep the LO instead, and the output of the mixer is all these different frequency products. So we will have the signal that we care about, the LO signal, and then on a first order, a mixer will give you the LO plus the signal and the LO minus the signal, and that's what these two smaller tones are for. And this is, I think it's this guy that we actually process through this filter. So again, I'll run it a couple more times. So you can see when that lower sideband goes through the filter, it shows up as a signal here. So let's run that a few more times. All right. So a question I get here, and I don't have a prize or anything I can award for you here, but we only have this signal going into the input of our spectrum analyzer, and that's represented by this guy here. But what about this guy? Man, that's a whole lot bigger than the signal we care about. Anybody want to volunteer where that comes from? Yep. That's close, yeah. So that's LO feed through, right? So that shows up when it's mixed in at the DC point. And so that's why our spectrum analyzers only go down to 3 hertz because, yeah, at the DC, boom, it's right there. So, I mean, this happens to all of us. You're looking at a wideband sweep on a spectrum analyzer, and you'll see this big guy down on the left-hand side, and you'll try to put the marker on it. It won't work, and what's going on there? And you know, you zoom in on, oh, it's my LO, right? It's DC. So that will always be there, and we do a lot of work to suppress that as much as we can. And just over the years, the lower end of a spectrum analyzer has continued to go down in frequency. But if you're new to signal analyzers, that's what that's about. All right? Okay, so just like we did on the signal generators, we're going to talk about some of the key things, key specifications that you want to look for inside of a spectrum analyzer. Again, different applications have different levels of performance that are needed. So we'll try to differentiate some of that for you because, you know, our data sheets are on the order of 50 pages long. So you want to be able to, you know, maybe not read through every single page, right? So we'll try to highlight the important ones for you here. So again, when you look at our data sheets, we tend to have 3 sets of numbers, and we try to bring that out. So specifications are basically warranted performance levels. So if you make a measurement on our analyzer and it falls short of these specifications, you can take it back, give it back to us and say, hey, you need to fix it or get me a new one or something because there's something wrong with this guy. So then we have typical values which aren't covered by the warranty, right? And they do represent typical values. We have a 95% confidence level. A lot of times we test for it, but we don't guarantee a particular level of performance. It's just, this is what a typical analyzer would do. So your mileage may vary a little bit, right? And so you'll see us put not only specifications, but typical, because obviously we want a little guard band, right, between what we guarantee and then what the typical performance is. And we tend to have anywhere from 3 to 5 dB of guard band in a lot of our magnitude specifications. So that's what that's all about. And then we'll give nominal values, and these are values that it's kind of a design performance thing. It's performance specification customers ask us about, but we don't test for it necessarily. So it's just what we expect to be the case. So one of the specifications is just the frequency range, and you can see here we designate this by different frequency bands. For those of you who wonder why an analyzer only goes to a certain frequency and stops 1 or 2 gigahertz short of where you need it, well, here's the answer, okay? So you can see that they basically represent different frequency breakpoints. Some of these are dictated by just traditional applications. Others are dictated by new applications such as wireless, which a lot of wireless is done below 3.6 gigahertz. So Customers have let us know that they don't want to pay for a 50 gigahertz analyzer when you only need 3.6 gigahertz of coverage. So we have different breakpoints in there to basically make it easier for purchase. So that's what that's about. It's also something useful to keep in mind. Sometimes, right, if you're doing a broadband sweep, you'll see a little change in the noise floor or something. Let's say the 8.4 gigahertz point or the 13.5 gigahertz point. Well, these represents frequency switch points. And so if you're operating at one of these switch points, it's good to know that, right? Yeah, these are just various things that contribute to the uncertainty of both the frequency and the amplitude measurement. Obviously, if you're looking at a signal and you put a marker on it, you'd like to know, well, how accurate is that? Am I within 2 dB of the power level that the marker says? Am I within half a dB? And that's something that has been improved on a lot over the years as we've gone from analog circuitry to digital circuitry. So another thing that customers are always interested in is magnitude and frequency accuracy. They're interested in the absolute amplitude of a signal as well as the relative amplitude of two signals or more as they relate to one another. So the relative amplitude accuracy always tends to be a little more accurate than the absolute amplitude accuracy. Anyway, but again, we've made a lot of strides over the last, since 2000 when we went to a fully digital IF processing chain, where we've really been able to get the amplitude accuracy down from 2 dB down to a few tenths of a dB, especially at the lower frequencies. So frequency readout accuracy, this is something you'll see in our data sheet. So you put a marker on the signal and you want to know, well, okay, that says 1 gigahertz. Is that within 1 megahertz, 100 kilohertz, 1 kilohertz? How accurate is that? Because I have a specification I have to measure to. So in our data sheet, we will give you this formula that shows that the accuracy of the marker readout is the marker frequency times the frequency reference accuracy. So we give you those numbers times 0.1% of the span, 5% of the resolution bandwidth. It's kind of a fudge factor plus the residual error. And you can see this horizontal resolution is defined as span divided by sweep points divided by 1. So if you were to go through that exercise and figure out how accurate is my 1 gigahertz marker on a 1 gigahertz signal with these operating parameters, you can basically plug and chug the equation, and you can see that for this setup, that at 1 billion cycles a second, I'm basically within a kilohertz, right? Plus or minus 900 hertz. So when you look at that, let's say your requirement is your accuracy needs to be within 500 hertz. So what could you as a user do to improve the accuracy of your measurement here, right? So you're not going to go in and change the crystal oscillator, right? You're not going to go in and solder and play with that. So what sort of inputs can you do as a user to improve that? Yeah, I'm sorry, a couple of, yep. So you can make the span a little more narrow, right? So that will improve that. So let's say you move that to 200 kilohertz. That would reduce that uncertainty to 200 hertz. Yep, so.
Decrease the resolution bandwidth?
I'm sorry?
Decrease the resolution bandwidth?
Yep, so you can lower the res bandwidth as well. So again, instead of 3 kilohertz here, maybe you make it 1 kilohertz, and so you would reduce this uncertainty from 150 to 50 hertz. And the nice thing here is in more modern spectrum analyzers, we actually have a special frequency counter algorithm that you can put on these guys, and they greatly improve the accuracy. They're not quite as good as just standalone frequency counters, but they are really good. So you might want to explore that if getting absolute frequency accuracy is important to you. And so here's just a slide that just talks about all the different mismatches. Again, on the input impedance mismatch, if you use a little more attenuation on the input attenuator, you can improve that. Yeah, I'll just leave it at that. So another thing you can look at is display fidelity. And a lot of these slides are talking about the way it was, let's say 20, 30 years ago versus the way it is today. So used to, the rule of thumb is if you wanted a really accurate signal or amplitude measurement, you had to put that signal right on the top reference level. Well, today, you don't have to do that, and you'll be just fine in terms of your amplitude accuracy. And again, the analog circuitry kind of needed that, but today's digital IF really takes care of that a whole lot, to the point where it kind of summarizes it up down here. And this is actually even an older, this isn't our newest guide, but yeah, it's a 10th dB versus on the green screen type analyzers we used to have, that was 1 dB amplitude display fidelity. Whoops, fat fingered it. So here's another source of inaccuracy, is just changing your reference levels. So that's when you change what this line at the top represents in terms of magnitude. That course, that's also called IF gain uncertainty, so you might see that in the data sheet. And again, kind of the story is you don't have to put the signal at the very top. So we've kind of talked about this a little bit, but we're going to talk about what all goes into resolving a signal. And so here you can see we have resolution bandwidth, we have resolution type, as well as selectivity, which we'll talk about, and we'll talk about these noise sidebands here. So again, this picture is really nice because it shows two signals and just the difference. I'm not sure what this resolution bandwidth is here, but you can see this one is 10 kilohertz res bandwidth. And basically the way we define what is the bandwidth of one of our res bandwidth filters is just when you have two signals of equal amplitude, when you start seeing a 3 dB dip between the two, well, then that's your resolution bandwidth. So that's kind of the industry standard definition. Another thing to look for is basically the shape factor or the selectivity. So here you can see if you compare the 3 dB bandwidth of the filter to the 60 dB bandwidth of the filter, that this results in a shape factor of 20. And that's pretty wide. And you can see how that kind of comes into play here. Again, the older analog shape factors of analog filters were roughly 15, 20 to 1. The newer digital guys are better than 5 to 1. On our X series signal analyzers, they're basically 4 to 1. So you really get a lot of, this comes, I don't want to call it a brick wall filter, but it comes down pretty quick. So the implication of that is if you have a signal right here, the old analog filter wouldn't see it for a particular res bandwidth, whereas the newer guys would. So that lets you get by with a bigger res bandwidth and not take a big speed hit. So that's one of the benefits there. Again, we've talked about phase noise before. I think it's the same picture that we saw in the previous plot, but again, we're looking at a spectrum analyzer, and if you have something with bad phase noise, it can mask the smaller signals, preventing you from seeing this guy. So phase noise can do that to you. Again, going with smaller res bandwidth can also improve that. And I kind of alluded to this earlier. Res bandwidth does determine the sweep time, and again, there's the sweep time is proportional to the resolution bandwidth squared, 1 over that anyway. But you can sweep it too fast, and you'll generally get an error. The modern spectrum analyzers are pretty clever on that. If you are using an older one, you might not get an error signal. So kind of a manifestation is if you're looking at something and you see the frequencies kind of go off center, or if you see the amplitude decrease, this is kind of what that looks like. You'll maybe see this more often on a network analyzer, which Dennis talked about at the beginning today. But you can, especially for longer cables, right, you can sweep a network analyzer too fast and get some weird responses, and then you spend a lot of time trying to figure out, what's wrong. So slow down the sweep time if you suspect you're sweeping too fast. So again, these analyzers are pretty quick, and they're just showing the difference here between our older 8563E. You can see had a less sophisticated display here, but to do a 1 gigahertz sweep with 3 kilohertz and video and resolution bandwidth, it roughly took 280 seconds to do that sweep. And 3 kilohertz is a fairly narrow res bandwidth. I mean, we go all the way down to 1, but this is pretty narrow. So with our newer analyzers, we can do it in 2.3 seconds. And they're talking about the fast sweep option that's standard for all of our analyzers now. And then an FFT version of that is 1.9 seconds. And so again, this is kind of what I mentioned earlier, is that today's modern analyzers, we can do both an FFT sweep as well as a regular swept tune analyzer. And I'll probably mention this again, but typically a swept tune analyzer gives you a little better dynamic range. FFTs tend to be faster. Bandwidth is really, really tiny. Okay, so anyway, that's just something to keep in mind. All right. So aside from phase noise, one of the other kind of important concepts on a network analyzer is what you call dynamic range. So that has a few implications, but generally it falls into a couple of categories. Can I look at a small signal in the presence of a large signal? The other thing is, how small a signal can I look at? Okay. So the two big drivers of dynamic range on our spectrum analyzers or signal analyzers are what they call displayed average noise floor. What's the noise floor of the instrument? And then also, what is the intermodulation distortion of the mixer? So as I put in a signal into a mixer, like I mentioned, it's very nonlinear. So it's creating a lot of new signals. So when do those signals start to pop up and interfere? So we're going to spend the next several slides talking about noise floor and what's called intermodulation distortion, third order intercept. It has a lot of names that it goes by. So for displayed average noise level or the noise floor, that's basically represented by this line here. So if you don't have a signal applied to your signal analyzer and you set up everything correctly, you're going to get a flat line, right? And if you put a signal that is basically at the same amplitude as your noise floor, you'll see a little 2.2 dB bump. Okay, so that's when you know your signal and your analyzer are kind of right there with each other. When you have a little bump like that. So this is important, right? And again, the better your signal analyzer, the lower the noise floor. And depending on what industry you're in, some people operate near KTB, right? And they're trying to find spurs or non-wanted signals way down there. And so that's what displayed average noise level is all about. So you as a user can essentially impact the displayed average noise level that you see on a screen, okay? So there's a few things you have to do to set up the analyzer to maximize your performance. So first thing, and this is the easiest, is the attenuation, right? So think of signal to noise ratio. So if you attenuate the signal by adding 10 dB of extra attenuation, the noise floor goes up 10 dB, right? So if you're looking for something down, I know this is a noisy signal, but you've just impacted your dynamic range by 10 dB by adjusting the attenuation by 10 dB. And sometimes you have to, right? If you have a higher power signal, like I said, you can destroy a spectrum analyzer with 30 dBm input. So you're going to need to probably put 30 dB of attenuation on there to get it down to a decent level. So, but just keep in mind that you've decreased the dynamic range roughly 30 dB. So if you want to maximize the noise floor, or I should say minimize it, you use as low an attenuation level as possible. Okay. So another one is the IF bandwidth. And so you can see as we decrease the IF bandwidth by a factor of 10, so we go from 100 kilohertz to 10 kilohertz to 1 kilohertz, we basically decrease the noise floor 10 dB. So we get a much, right, this isn't a very satisfying picture, right, if you're just looking at a little bump here. But then as you lower your resolution bandwidth, you get much more resolution. And obviously, if you have a spur or unwanted signal here, you'd be able to see that with the 1 kilohertz res bandwidth, where you wouldn't be able to see it with the other one. And so what we do, and what everybody does, when you talk about the displayed average noise level specification, it's usually normalized to 1 hertz, because otherwise one guy would do it at 100 kilohertz, another guy would do it at 10 kilohertz, and oh, my noise floor is better because I'm using 10 kilohertz. So to get by all of that, right, you just use a 1 hertz IF bandwidth. And again, that's some functionality that you can get off of the signal analyzer. Then you can also use trace averaging or video bandwidth filter. And again, that'll let you see a signal much closer to the noise floor. So let's put some of these concepts together. So if you look in our data sheets, and we actually, there's going to be another line here that we'll go over in a few slides, but we basically give you this information. And yeah, this should really be displayed average noise level, and it's so many, anyway, we'll just leave it here. But you'll see these different lines, and they basically are the displayed noise for a given resolution bandwidth. So you can see this has a line for the 1 kilohertz res bandwidth. This is the line for the 100 hertz res bandwidth. And what the x-axis represents is the power at the mixer. So if you're putting in a 0 dBm signal, you can't just say 0 dBm. It's like, well, what's your attenuation setting? And generally, you know, you're going to have at least 10 dB, let's say, of attenuation because it helps your input match. So for this graph, instead of for your 0 dBm signal with a 10 dB attenuator, basically the mixer is seeing minus 10 dBm. So you'd use this point right here. And the way to kind of use this particular chart is you look at one of these levels here. Let me make the math easy on myself. So if I go on the y-axis here, this is roughly minus 60, minus 70, minus 75. So I go minus 75, and you add to that minus 50. That represents a roughly minus 125 dBm per hertz noise floor, okay? So I'll be able to see something along those lines, right? If you go up here, because we have a different resolution bandwidth, again, this is minus 60, and you come down here, and that's roughly minus 55, so that's minus 115. So there's a 10x difference in res bandwidth, so there's a 10 dB difference in the noise floor, displayed average noise level, right? And so if you do that across this line, all the values will be the same, and you do this across this line, and all the values will be the same. So again, that's why in our data sheets, we typically terminate it, set the attenuation to 0 dB, and put it for a 1 hertz res bandwidth and basically generate this graph. So here's a nice summary slide that talks about if you want to maximize your Dano performance, use the lowest res bandwidth, minimum input attenuation, averaging. You can also use a preamp, so this is a low noise amplifier that can get inserted into the signal path. That will definitely lower your displayed average noise level. In one of our models, we have what's called a low noise path, which actually bypasses a lot of the active circuitry. So this really works well for higher frequency measurements, so you can get between 5 and 10 dB extra noise floor performance. And then we kind of have another methodology here called noise floor extension. And if you want the ultimate performance, you can combine the preamp with the noise floor extension and basically get below KTB. We don't warrant it down there, but it's noise floor extension basically uses math models with some calibration data to take out the noise effects of the analyzer to get way down there. So again, don't have enough time to get into it here. There's a white paper on our website, and then they can demonstrate it to you at the booth. All right? Any questions on this?
On the setting the resolution bandwidth, so is there any guidelines, is that like independently from the video bandwidth, or you have to have a conversation with them?
Okay, so what are the guidelines in terms of using resolution bandwidth? Yeah. Well, the good news is that the simple answer is just use the defaults in the spectrum analyzer, and you'll probably be okay. But if you're near the noise floor, then you'll probably want to lower that video bandwidth. And basically, it's user preference. So, right, yeah. So the video bandwidth, I mean the resolution bandwidth, think of it as working on the signal, and the video bandwidth cleans up the trace. Okay, so that's, maybe we talk about it afterwards because that's a completely different thing. But we can, so first of all, it's a completely different mode. So if you want to think of it as an app or a personality, but that's usually an extra option, right, where we have a noise figure mode, and that includes different software, right, but it uses most of the same hardware because, right, a spectrum analyzer is a very sensitive receiver, but it also has some special noise source voltage sources, typically in the back of the analyzer. So it has to, basically, this is kind of an advanced question, but when you have a noise source connected to the signal analyzer as a noise figure meter, it will turn the noise source on and off, so you get the hot energy and the cold energy, and then it's able to do the math to see the difference between the two and give you both the gain and the noise figure. But there is extra hardware to turn it on and off. You would need a noise source, and then you would put that into the input of your signal analyzer to calibrate it, and then you put your device in between the noise source and the analyzer to make your measurement. Does that answer your question? Okay, great. Okay, so in terms of dynamic range, we kind of covered noise floor, right? And because a spectrum analyzer made of active electronics, you're going to have, you can only go so low. Well, the other part of it is just the fact that the heart of a signal analyzer is a mixer, which I mentioned is a nonlinear device. So when we look at the RF input, and it looks like this, depending on how things are set up, and of course the imperfections in our receiver. Not only will it translate the frequency you want to translate in frequency, it will also add some of its own distortion to the measurement. So if the signal looks like this, you might see something like this on the analyzer, and maybe your specification says that the difference between this and this needs to be more like that. So then you look at this and you say, well, what's wrong? Is it my part? Is it my setup? What's going on? So let's talk about some things to think about in terms of minimizing distortion for the analyzer. So let's make sure we get some definitions down. So two of the more popular distortion measurement types are two-tone intermodulation. So that's where you put in two equal amplitude signals. They generate these third-order products, and you figure out, well, how far down is this? And then the other is harmonic distortion, where let's say this is 1 gigahertz and 2 gigahertz, 3 gigahertz. If this was a square wave going in, this would be 1 gigahertz, and maybe this would be 3 gigahertz, 5 gigahertz. Only the odd harmonics would show up. So the key thing to think about is that as the power goes up on the fundamentals, if you increase this 1 dB, then your third order products will go up 3 dB. So if I increase this 2 dB, this will go up 6 dB. Same thing on the harmonics. The second order harmonic here goes up 2 dB as this goes up 1 dB. The third order product goes up 3 dB as this goes up 1 dB. So keep that in mind. So again, the absolute change is 1 dB here and 3 dB here. But the relative change is only 2 dB, right? So as this goes up 1, this goes up 3, so the delta is 2, right? So why do I talk about that? Well, because we've got something in our data sheet where we take advantage of that. So you'll see this graph in our data sheets as well, and this is the distortion that is created by our signal analyzer versus the power at the mixer. So again, the power at the mixer is your input signal minus your attenuation. So it's how much power actually hits that core mixer, right? So what we can see here is that if you hit our mixer, in this graph with minus 30 dBm, right, you'll start to see distortion, third order distortion products, because I'm on the third order curve, of roughly minus 70 dBc, right? 70 dB below the carrier. So again, depending on your measurement, you need to make the appropriate adjustments. And then one thing you'll notice on the graph here, remember how I mentioned that the relative difference between the fundamental and the third order product is only 2 dB? Well, you can see that here. So for every 1 unit of change on the input power, the third order product went up 2 units, right? So that's why I kind of made a big deal out of that. So you can actually see that in the graphs. The second order curve, right, it's a 1-to-1 relationship. So that might not seem intuitive at first, but that's kind of what's going on there. That clear to everybody? Because that's kind of a key point. And, so to make sure that you're not generating something internally, internal distortion, one easy way to look at that is just change your attenuator by 10 dB. And if we're not causing the distortion, you'll just see everything basically move up and down 10 dB. If we are causing the distortion, you'll see your signal will change in amplitude, right? So that's a quick and easy test. You can look at the data sheets as well. And then this graph, this is what you will actually see in our data sheets, right? So you'll see our displayed average noise level here. You'll see our second and third order products here. And basically, from a dynamic range standpoint, this is your optimum point right here. So if you're wanting to avoid third order intermod products, you'll want to operate it right here at roughly minus 35. So let's say your signal is minus 10 dBm. You'll want to put roughly 25 dB of attenuation on there to get it at this super good point here. And one thing on our spectrum analyzers, you just had 10 dB of attenuation. So you either, right, so you couldn't center it maybe on this point here. You either had to choose minus 30 or minus 40, right? One of those settings, let's say. Well, today's spectrum analyzers have 2 dB of attenuation. So you can really get really close to the sweet spot of your analyzer. And so whatever measurement you're making, take a look at the data sheet, right? Figure out where you're at here, and you can make optimum dynamic range measurements. Okay, I'm running a little over on time, so I just wanted to, let me just go here. So that was the old days, so to speak. Old days being till 2000. So basically what we've done in modern signal analyzers is we've replaced this entire IF chain with something totally digital. And so the amplitude accuracy's been improved, the speed's been improved. Again, we give you kind of 2 analyzers for the price of 1. You still get your traditional swept tune analyzer, which is great for dynamic range. Then you also get an FFT analyzer, which which is great for narrow res bandwidth. So here's just a typical block diagram and some typical specifications. Another point is, here we're looking at our specification and then our 95% confidence. So we're 95% confident your amplitude accuracy would be 0.2 of a dB versus the older analyzers, which were at 2 dB. And then one of the nice things about the modern analyzers too is a lot of these measurements, used to you had to set everything up by hand or run a program and do a lot of post-processing. Well, a lot of those functions are built in, so I talked about ACP. It's a one-button measurement. Third order intercept, that's a one-button measurement. This is really spur search, so spurious emissions. It'll help you find signals that you don't want. And then these are the extra personalities that I talked about. Noise figure was mentioned earlier. We have phase noise, analog demod for AM, FM, phase modulated signals. We have flexible digital modulation. That's for the basic digital demod types like QPSK and 16 QAM. And then because wireless communications is so prevalent and it's so algorithm intensive, each of those guys has their own personality. So if you're doing something like Bluetooth, you're doing something like LTE, that too has a dedicated personality. All right, a lot of marketing stuff here. So I will, I think, leave it with that. This is our kind of current portfolio. This is new guy, our newest guy. If you want to see you've always wanted to have a signal analyzer that drives like an iPad or a tablet. This is the first guy that does that. So it has a capacitive touchscreen versus a resistive touchscreen. So you can pinch and zoom. You can do this with the trace. It's a lot of fun, and it's our highest performing analyzer. And it's got a 14-inch screen, so a lot of other good stuff in there too. So anyway, that's all I have. Thank you for attending. If you have any questions, I'll be off to the side. We got to keep going. So anyway, thank you very much for attending.